Alright, this is video 2 for the lifting unit. So in this one, we need to start talking about torque. When we want to start calculating how much weight a motor can lift, torque becomes very important. We discussed earlier that torque is a force directed in a circle, like a spinning force. So this torque applied to a wheel can create a linear force at the wheel's edge where it touches the ground. So looking at this, we see we have our applied force, there's a torque, and then this wheel has a radius. So torque is equal to a force which is perpendicular to a lever arm distance. So when applied to a wheel, the torque equals the force that's applied to the ground times the radius of the wheel. So the way we calculate torque is a force multiplied by a perpendicular distance. So looking at this example right here, we see that we have a 30 Newton force. We have a lever arm distance of 0.5 meters. So we see that we need 15 Newton meters of torque to pick up that 30 Newton ball. So the motor would have to maintain that 30 Newton meter, or that 15 Newton meters of torque. If we take a look at the VEX 393 motor though, we see that it has a stall torque of 1.67. So just going back through these numbers here. Remember that the free speed is the speed of the motor with no load placed on it. The stall torque so that's the amount of load that will stop the motor. Remember that load is external torque placed on a motor. The stall current that's how much current is drawn from the battery when there's no load. And then I'm sorry, I got these backwards. Switch those. The stall current is how much current is drawn while the motor is stalled, and the free current is how much current is drawn when there's no load. So we can see that since the 393 motor has a stall torque of 1.67 Newton meters, it would not be enough to handle this task. 15 Newton meters is too great for a single 393 motor to handle this. Okay, so we can go a little bit further. We can also try to start calculating how much force the motor needs to apply on an object. So in other words, how much will the 393 motor lift up? How much force can it lift up if there's no gearing attached to it? So if I were to take a look at this, it looks like it's just a regular rack and pinion style elevator. So we would have our gears, our linear gears, and then we would have our pinion gear attached to this. So looking at this then, torque equals a force which is perpendicular to a lever arm distance. So in this case, we'd have torque, which is equal to a force times the radius of the gear. So the force would equal torque divided by the radius of the gear. So notice that we want to use smaller gears, something I mentioned earlier. Okay, so torque of these motors is 1.67 Newton meters. The radius of a 12-tooth gear, our smallest gear, the radius is ½ of an inch. So we need to convert the 0.5 inches into meters. And we can use some approximations for this. There are two. So we need to convert that 0.5 of an inch into meters. Now, one thing I know is that 2.5 centimeters equals 1 inch. So then ½ of an inch would be 1.25 centimeters. So in terms of meters, we'd move the decimal 2 places. Our 12-tooth gear then would have a radius of 0.0125 meters. So when we type this up, we find that we can lift with a force of about 130 newtons. That seems like quite a lot. Another quick conversion is that there are roughly 5 newtons to 1 pound. So if I take that 133.6 and divide it by 5, I see that's right about 26 pounds. Yeah, that's nothing to sneeze at. It's probably not as much force as you might think, but that's still not too bad for a little tiny motor. Okay, the next topic is shock loads. So what exactly is this? A shock load is an instantaneous spike of loading on some sort of mechanical system. So imagine if someone grabs onto the arm of a robot and pushes down on it as hard and as fast as they can. As you might imagine, there'd be some gears grinding, there'd be some teeth broken off of the gears, probably do some damage to the internal parts of the motor, might bend some metal on the robotic arm. There's a lot of damage that can happen from a shock. Now, obviously, I don't think anybody would intentionally damage your robot, but what if it fell over? That could definitely have a shock. What if you're trying to pick up something that's too heavy? So there's a lot of things that can damage these. So how can we reduce the amount of shock? Really, the best way is to run multiple gears. You may have noticed this already. When you take a look at a gear train, when you have lots of gears on, let's say, a robotic arm, it has a little bit of give to it. It can move a little bit before it ever moves the motor. So, and this just comes from the fact that there's a lot of gears in there and they each are turning a little bit, which leads to a large result. So by running a gear train, this will reduce how much shock that a robot may experience. Now, you won't be able to get rid of all of it, but it will help. All right, next topic is a 4-bar linkage. So a linkage is it's another way of like converting input to output motion, and it's very similar to a scissor lift. Now, a 4-bar comes from the fact that there are, well, 4 bars. So here I have 1 bar, 2 bars, 3 bars, and 4 bar. So that's why we call this one a 4-bar linkage. Now, in a 4-bar linkage, or any linkage, you always have a fixed link. So that's one that's attached to, let's say, a tower. And you always have a driven link. So that's one that's attached to a motor or a gear train of some kind. And what's nice about these systems is as you drive them, let's say you have like a platform, like this is your tower, and then you have like a platform on the end of this. The platform, if you work on your geometry, can stay nice and parallel to the floor at all times. Now you can play around with the geometry with these linkages to get some unique outcomes. Over here to the right is a picture of a linkage that I built. So if I were to try to count this one up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this right here is a 10-bar linkage that I built. And when it's completely down, if you build the geometry right, they really squash up like an accordion, and then they reach out. And this one, it was able to pretty much touch the ceiling. I ran it with 2 motors and a compound gears train. So it was pretty easy to run. But linkages are a nice way to get great heights in confined spaces. You'll see a lot of teams, if there's a lifting part to it, there's a lot of teams who like to use a linkage. And 4-bar linkages are kind of small, but you know, you can go up to 6, you know, as far as you want to go. All right, the last topic is passive assistance. So when a designer adds something to the lifting mechanism to assist the actuator, remember actuators like a motor, and lifting the load, they usually take the form of like a counterbalance or a spring. So passive assistance is something that is non-electrical. It does not use any of the robot's power. And its purpose is to reduce the load that you place on the motor. So let's take a look at this example. This is a huge manipulator, and it's being run with a rack and pinion system with a single motor. Now that single motor probably would not be able to lift that up. However, notice that the designer added these elastic cords on the back. Those elastic cords by themselves are not enough to pick up this load, but the motor working together with those elastic cords is able to. So those elastic cords are not meant to pick up the load by themselves, they are just meant to assist that motor. Another thing you could do is putting a lot of weights, so like putting a bunch of pieces of metal on this side, act as a counterweight. That would probably help as well. And with this this design here, it's kind of a unique design. I think it'd be kind of a unique thing to see someone try to build something like this. It looks like a dinosaur to me. The next time you go home, if you have a garage, take a look inside your garage and you'll find some passive assistance. There are these garage door springs that are used to help take some of the load off of the garage door motor. So we see these passive assistances in a lot of different areas. All right, that's going to conclude our lifting mechanisms unit.